Okay, so I welcome all of you once again for this basic electronics class on today's lecture. And as I was just briefing all of you that today we are going to start off with a new module, the module 2 of the syllabus. And that is basically the starting of this topic, to be honest. So let me directly go ahead with what we have done and what is in store for us. So this is basically if you observe the first portion of it, this is what we had discussed up till this point. So we had discussed the first module where the basic components, the power supplies, the function generators, multimeter, series parallel connection, color coding scheme. Mostly some of the concepts you might be knowing already, some of the concepts which we had started off. So those things we had discussed over here. And now we come to the module 2, where we are actually discussing junction diode. Okay, so this is a part of our second module, and as you can observe that topics we will go one by one as we finish off on time, but we have only 4 hours of study. That's the problem, because we have to fit in many things within these 4 hours, but I'll try to come up with specificity, like how we can manage out of it. But let's see, if it requires more time, we will take that also. But this is basically the module on junction diodes, right? So this is the starting of it. So basically, when we start off this module, ideally, the objective is that uh, when we consider this, I think pretty much known to you already, that ideally when an atom we are considering, it will usually have three types of particles. Okay, so we have the electrons which are negatively charged, we have the protons which are the positively charged, and the neutrons neutral. So we are not bothered with much of the neutrons for the time being, because electronics deals with electrons itself. So the negative charge ions are the most important one for us. But in that also, we are observing that when we are considering uh, the, the nucleus, okay, and the electrons will revolve around the nucleus in different orbits. I think all of you know that. Now, if you observe in this particular diagram itself, that this arrangement of the electrons are also mapped by a specific number and a specific order, and that is given by 2 to the power n square, rather, 2 to the power n square, where n is an orbit number. Right, now this orbit number, like if it is 1, then basically we have 2 electrons. You can see the 2 electrons which are present over here. But if it is more than 2, like the second orbit, if you consider, so it's 2 to the power 4. So 4 into 2, 8. So there should be 8 electrons in the next cycle, like that, so on and so forth. All right. Now, in this way, if the orbital electrons are placed in that, the last portion or the last ring that you're observing over here, at least for this particular diagram, if you observe, this is what we call as the valence shell. All right. So this is the outermost orbit which you are looking at. And in that orbit, the electrons which are residing in that orbit, we call it the valence electrons. This happens to be the key element to all the discussion on semiconductor devices. All right. It happens to be the key aspect, key criteria on which the whole of the PN junction and N junction, P junction diodes, even after that also, like when we go for the transistors and everything will match with respect to the valence electron. Why? Because this valence electron which resides on the outermost shell are the most energetic and are involved with bonding and charge transfer. Right? So that is very, very essential, because this bonding and charge transfer, this happens to be the key to all the elements that we are talking about with respect to diode. Any characteristic, whatever we are going to discuss, is done with respect to this. Okay? So if you observe carefully that when we are talking about this, when these valence electrons we are talking about, so there is a these are outward, right? They're outside uh, they are the outermost electrons we're talking about. So basically, what it means is also that the attraction towards this nucleus, okay, which happens to be the neutron and proton, so it is far ahead. It's going away. Okay, it's far apart. So what happens that if I, like, you can imagine in this way, like if I can energize these electrons to some extent, so that these electrons, as they're already energetic itself, so what they might do from the valence shell, they might go up even further towards the conduction level. I'll come to that. Okay. And if it reaches the conduction band, that is, there is always a possibility that that will start to conduct electricity. All right. So that is basically the role of the valence electron and the different bands associated with it. We'll come to the bands later, but this is basically, you can see the last line. Absorbing energy, electrons move to higher energy levels and lose energy when they return back to original level. This is given by 1 eV. We call it the electron volt. Okay, I guess some of you might already have used this term somewhere. So what is the first slide indicates that there are electrons at the valence level electrons, valence band electrons we call it, and those valence band electrons, if they are energized at a certain level, and if it is possible, because you will soon find that it is sometimes not even possible, even if you have valence band electron, but it won't be possible for those electrons to go towards the conduction band. All right, so that will also happen. But whatever it is, but given a circumstances, given a favorable circumstances, this valence electron can actually move to a conduction band, and the conduction band, by that what the term indicates that we can use that conduction band for the purpose of conducting the electricity. Like, since the electron is going to the conduction band, it will conduct the electricity. Okay, you can imagine that way. All right, so that is the first. So valence electron is done. Now, as I was discussing, now suppose when the electrons, when the electrons are orbiting, okay, across it, we are calling them in terms of our discussion as energy bands. We are only focused on that. So if you observe carefully in this particular diagram, the valence band, we are calling it as a band. So it's a band of energy. It's not that a specific value or something like that. It's a band of element where all the electrons are residing. So all the valence band, they will have their own potential energy, they will have their rotational energy, they will have the magnetic energy and all. Okay, so this is all together, those energies forms the valence band, and the electrons are residing over here. Now, if you carefully observe that there is something called as, in the right hand side, forbidden energy gap. Okay, and this forbidden energy gap is the amount of energy that this valence band electron would require in order to jump to the conduction band. You can see the conduction band over here. Okay, so that is the basic principle in which all the semiconductor devices would work. All right. So this formation, that this energy band formations are the closely spaced energy level, and they form the energy band. Clear? So valence band. So you can see that here first band, second band, these all exist. There are all, the other electrons are also there, but they are closely knit to the nucleus. You can see the edge of the nucleus. Okay, so after the edge of the nucleus, there are other electrons which also possess some amount of energy, but they are very close to nucleus and they are residing, suppose, here. Then we have a second band that is also there. But the more we go downward, it is impossible to get those free electrons or get even some electrons where it can penetrate to the conduction band. The amount of energy that will be required as a source is impossible. So we cannot that's not a practical solution at all. The only solutions can be that if the valence band electrons can get excited by some means, and if this forbidden energy gap, you will soon find that this is also very important, it will actually change. If this forbidden energy gap is also possible to overcome, then only we will have sufficient energy, sufficient electron in the conduction band. And if it reaches the conduction band, those electrons definitely can have a charge transfer, or in a way, the current conduction through the whole circuit. Right. So if I can make a device where this property is utilized in making sure the current is running through it, then that is basically the junction diode, or the principle of any semiconductor, to be honest. We'll see the differentiation later on. Okay. So this is the first half. So we have done the valence electron part. Now we understood that what is energy band as well. Okay, how the energy bands are associated. Any doubt till this point? Anyone? Anyone having any doubt?
No, sir.
All right. Okay. At least respond. Okay. Now, if you observe that this is already we have, I have already told you. So you can see that there are three specific diagrams that we are talking about, and that is where the band gap comes in. So valence and conduction band, we have already told you, I already have told you what exactly it is. But now if you observe valence band is that where electrons are more attached to the atoms compared to the conduction band. Now this electrons which are there in valence band are ideally non-movable. They won't move freely. But given an excitation and given, as I said, this band gap is sufficient enough, okay, that we can overcome, these non-movable electrons or non-movable elements can move to conduction band where electrons are least attached to the atom. Okay, and that is influenced by an external force. So we can add external force. Here is a potential. We are adding some potential. We are adding some voltage source or something or power source, something like that, which will enable the movement of the electrons. And as naturally, the current will flow into opposite direction. So if you observe here carefully, we have categorized based on the energy band. We can categorize these materials into three halves. Okay, although it is there in the next slide, but at least I'll give you over here. If you observe carefully, this particular left-hand side diagram is for the insulators. Okay. Suppose, for example, wood or a glass for that matter. What I was mentioning is just see the common diagram in each of the three. That this blue sky blue color portion is the valence band, and the valence band has sufficient amount of electrons present in all three. But if you observe in insulator, the band gap that you are observing, is maximum compared to the other two scenarios. Okay, so that is what makes an insulator. That it is impossible, okay, for an insulator, or if it is an insulator, that the valence band of electrons will penetrate through the conduction band. This will never happen. All right, so that is basically makes insulator different to that of both the conductors. Conductor is just the opposite to insulator, because if you observe here carefully in the right hand side diagram in here, okay, last diagram, you can observe the valence band and the conduction band are almost overlapping in nature. So what about the band gap? You can see that there is a question mark I have given, that because there is very little band gap which is present. In fact, it is almost overlapping in nature. So what happens that given a particular power like source or external force, we actually have the electrons which can jump from the valence band very easily towards the conduction band. All right. So that is basically where what it makes a conductor favorable. For example, the copper wires that is used for daily purpose, a very common example. Now coming to semiconductor, which is our part of our study, is somewhere in between these two bands, where you can observe that definitely the overlapping scenario between the valence and the conduction band is not available, but there is a band gap which is present. But this band gap, okay, this band gap can be achieved. This is usually like 1 eV or something like that, very small band gap also. So this band gap can be achieved quite easily using the external power supply. So what will happen that you can imagine that during a normal process or normal if you are considering a semiconductor, it will behave as an insulator if you are not applying any external force or external source for that matter. But if you are providing an external source, then the same insulator material will act as a semiconductor, because the valence band electron will jump to the conduction band and will start to behave as a conductor. So that is the brilliance of the semiconductor and specific materials like the silicon, the germaniums and all, which has this specific property by where that is utilized for developing all the diodes and semiconductor devices for the world. Okay? So that is basically given in the second, sorry, over here, you can see that these are the material classification. I have already told you all the things. Just to brief you again. So you can see for the insulators, there is no free electrons. Simple as that. And I can see high forbidden gap. High forbidden gap. You can see over here. Okay, it's around 6. Its EG should be greater than 6 electron volts. It's a huge amount of impossible. In fact, that's not a possibility. In fact, And you can see the examples of the glass, ceramic, but that is the reason. The principle behind it is because of this. Okay. Similarly, conductor, you can see no forbidden gap, or it's an overlapping band we call it, and we have an example of copper. All right. Whereas in case of semiconductors, you observe partially filled conduction band and valence band with narrow energy band gap. Narrow energy band gap, and these are the materials as I was telling you: the silicon, the germanium, okay, the tin, SN is tin. These are the materials, some of the materials. There are few more in fact, but these are the pure materials which actually exhibit this property. Now, if you observe very carefully, the beauty of it is that conduction band, there is no electron at 0 degree Kelvin. Okay? But the valence band is of full electrons. Now, if we are making sure that temperature changes, due to temperature, the Fg is the band gap, forbidden band or forbidden gap or like that. So this is decreased and electrons are liberated to the conduction band. So it is a kind of switch on off process, if you can observe carefully. So we actually can make sure that how much or what we are expecting at the output, whether we are allowing the output to happen or we are not allowing the output to happen. So very clearly you can observe that using a semiconductor, we can actually think of it as a kind of switching option that we can have. We can have a better control over the flow of current or the flow of circuit. All right. So that's basically what the material specification or classification is all about. Now, as the insulator and conductor is not the part of our syllabus and we are not much bothered with that, the semiconductor, if I consider, that can be classified into two halves primarily. One is called as the intrinsic semiconductor and the other one is called the extrinsic semiconductor. Now, if you see this particular table, it's very clear, intrinsic is over here and extrinsic is over here. By definition, what it means, that is what we are going to discuss in the next slide. But ideally, what is happened, if in general we can say, intrinsic semiconductor is a pure form of germanium or silicon. We have established by now what is valence electron, what are the energy bands, okay, how the energy bands are placed for different materials, and how the potential, the forbidden gap can be achieved for the semiconductors. So now, as we have established what is semiconductor or what is the property, fundamental property of semiconductor, in intrinsic semiconductor, we are considering that if it is a pure semiconductor or pure material of germanium or silicon is what we are using. Or the other option is if there is an impurity that comes in with the pure material. All right. So that is basically what we call as the extrinsic semiconductor. So if I just happen to point out over here, so intrinsic semiconductor is basically pure semiconductor. Okay. Whereas the extrinsic semiconductor is impure semiconductors, can say in that way, because there will be a process in which the extrinsic semiconductor will work. All right. So you can observe that. So this is basically the classification within the extrinsic semiconductor is the most famous N-type and P-type extrinsic semiconductor. N-type is separate, P-type is separate. N indicates prevalently. You can see prevalently it's a electron is more. Okay, electrons are more. That's why it's called as donor impurity. I'll come to that next slide. And P-type is basically called as the holes, where the holes are the carriers, majority carriers. We'll see that one by one. So this is the basic classification. I'll come to each and every detail. Now we come to intrinsic semiconductor. So we have established what is semiconductor now. So now if you observe an intrinsic or pure semiconductor or undoped semiconductor, this word is crucial. It's a key word. Okay. Undoped semiconductor is a pure semiconductor without any significant opened species present. So this is a pure silicon. If you observe over here in this particular fabrication or in the atomic level diagram, all the atoms are of silicon. Si. Right? So this is all the silicon, and this dots you are looking at, they are the electrons which are present. Right? So this is a pure semiconductor. So forget about what is insulator for the timing, forget about what is conductor for the timing. So we have to understand that for the timing, we are assuming a semiconductor. So the valence band and the conduction band both are partially filled. This is the scenario we are in. Or rather, at this initial stage, we would consider the valence band only is filled with electrons and the conduction band is nil. To be honest, because at room temperature, if T equal to 0, it behaves as an insulator. You can see the second line. It behaves like an insulator. But at room temperature, when it comes at 300 Kelvin almost, some of the valence electrons have enough energy, thermal energy. We call it the thermal energy. So that thermal energy will make sure that the covalent bonds are breaking inside the molecular state, and this free electrons will have the enough energy to gain certain amount of energy. So this 1 point, that EV that you were talking about, the amount of small value of forbidden gap that we were discussing with respect to semiconductor, the free electrons will be enough or energetic so that it goes on top of that forbidden gap, reaches to the conduction band. All right. So if you observe in this particular diagram, in this specific segment, few important points we are there. One is you can observe that these are the free electrons. You can see this over here. All right. So these electrons are free. Now, whenever these electrons are free, whenever we are considering the electrons are free, definitely the electrons, why their electrons are free? So the from the valence band they have come out of and they have reached the conduction band. So now, whenever we consider an electron, in order to balance thing out, we have to consider that whenever there is more number of electrons, electrons are negatively charged. So in general, the total polarity of the electric, you can say the electrically it should be neutral, right? So in order to consider that, we need to have the holes as a concept, which is nothing but a virtual concept. You can just write it down over here. Okay, it's a virtual concept of holes which was introduced, which is nothing but a positive element. Okay, so ideally the scenario is the number of electrons that you have and the number of holes that you have should be equal, because then the electrical neutrality should be maintained. And that's why whenever we have a free electron, we would say that there is always a free hole also. So that is where the term comes in, that electron hole pair. Okay, so when we have a free electrons, definitely it is something like I usually imagine that way, that suppose you have how do I consider? You imagine that game. Have you played that game called Brain Beta? Have you ever heard that, with the marbles we used to play? All right. So what will happen, that there will be a structure like this, and there will be some small little dots like this. The marbles will be placed like this, and there will be one position which will be empty. So what the game is that we have to remove this marble over here, okay, and we have to adjust accordingly one after the another, so that the arrangement, we keep on doing that until and unless we come to a smallest number of marbles present in that disk. I don't know how many of you played. Have you played this game? Brain Beta, we used to call it. Don't know.
Yes, sir. Yes, sir.
Same thing. The same thing happens over here. That one block at the initial stage, supposing that is a free electron, suppose at some point thermally generated. So in order to do that, the index electron, when it goes out like something like that, there will be a equivalent positive response that will be generated, as if we are plucking one marble from one socket and we are removing it. So that socket remains empty. So that's the hole. The hole ideally is not a particle. Electron has it has a particle. Hole is not a particle. It's a virtual neutral element or positive element, which is just there to compensate to maintain the electrical neutrality. So whenever we will call a N-type semiconductor, we would say that it has the majority of electrons. So that's the first concept that we are talking about, is a majority and minority carriers. So in I think I got disconnected. Most probably. That's why I stopped a little bit. Am I audible right now?
Yes, sir.
Yes, sir.
Yeah, I think I got disconnected. I just happened to see this. So what I was talking about, that this is basically what happens. So the electron and hole pair is a combination. Okay, so it is like together. Now the more the electrons are generated, the more similarly some holes will also be open to accept it because holes are positive. In that way, what will happen eventually? What happens that the thermally generated electron and the holes will collide among themselves. Okay, and this collision is called as the recombination. You can see over here. This recombination will also generate amount of heat. Later on, we will observe that this recombination at the junction diode, the one where we actually are heading towards the junction diode, this will be acting as a heat, and some changes will happen to the overall current calculations and all those things. So we will see that. But this is basically what we call as recombination. So the electron and the hole will recombine together. All right. A very small time before which the recombination happens is called as the mean lifetime. Okay, so that's called as a mean lifetime. So it is usually ranging between 1 to 10 to the power 3 microseconds. So you can imagine the small time that we are looking at over here. So in summary, for an intrinsic semiconductor or for a semiconductor, what we are looking at is that total current is nothing but the electron current plus the hole current. So total current needs to be considered in that. It's not about only electron that is possessing. It's electron plus the hole that we are looking at. So it's something like this, if you observe. So if you observe in this diagram very clearly, so we have a potential over here. Now the free electrons are running this side. You can see this red are the electrons. So if they are moving this side, okay, like this, the direction that you're looking at, the holes are actually running in the opposite direction. And why it is a favorable condition? Because the electrons are negatively charged. Now you can see the supply that you're giving, this is positive and this is negative. So basically the holes are getting accepted or as if it is attracted towards the negative terminal, whereas the electrons are accepted towards the positive terminal. So you can see that there is a movement, there is a charge transfer and there is a current movement that is taking place. All right. So that is basic idea. This basic idea gave rise to all the concepts related to junction diode. Even the forward bias, we will see that in a word, or even the reverse bias will work on the basis of this particular principle, the electron and hole pairs movement. All right. So this is about the intrinsic semiconductor. What other segment of the type, and the most important one, in fact, to be honest, because intrinsic semiconductor we are not going to discuss much, to be honest. So mostly the other part that we are looking at is called as the extrinsic semiconductor. Now in case of extrinsic semiconductor, what happens that you can see that it is not the pure one. So the semiconductor that we are considering will have to be doped. You can see the word over here. An extrinsic semiconductor is one that has been doped. Now, what exactly is doping? Now you can observe in this particular diagram that if you check the germanium ion over here, okay, we have 4 valence electrons. Okay, each of them has 4 valence electrons. And in the way, it is actually making some covalent bond together. You can see over here, all the germaniums are connected together. But in that whole crystal of germanium, we are doping a boron over here. Now, boron is acting as an impurity. And what is the advantage over here? You can see it's a trivalent compound. It has three electrons. So what will happen that eventually, whenever the covalent bond, this germanium ion is trying to make the covalent bond, this particular electron, you can see that it can't make any connection over here because it doesn't have any valence electron itself. All right. So in that way, what will happen? So we will have a. You can see in this. It was running. I guess I'll go back and show you. So you can see in this diagram itself closely that this is a free electron. It's moving. It's moving. Like that, it's breaking up somewhere. Now you can see there is a hole generated over here. As it generates one hole, another electron will come and try to recombine with that hole because it's a positive element. So this excess electron and the respective other process, the cascading process that is going on, that will eventually make a cascading feature in which more and more number of electron and holes will be generated one after the another. So one electron will lead to another electron will lead to another hole, and the hole will be again, and the initial electron that is generated will get combined with the hole. So like that, it will go on once again and again. So just using that impurity, we are actually introducing an avalanche of electron and hole pairs. So you can imagine that as we are discussing this avalanche of electrons and hole pair, indirectly we are indicating that we are actually making sure the current conduction is taking place in a circuit where this kind of a device or this kind of an element is being used. So I think the next slide will give you much clarity. So that is basically what we're talking about. So increase the conductivity of semiconductor, the impurity is added, and you can see that it is around 10 to the power 6 to 10 to the power 10 atoms of semiconductor. One impurity is enough. Just you can observe over here. Okay, so in this case, you can see that it's a pentavalent. So this is a pentavalent element. So this one is the same one that I'm talking about. But if you observe over here, these are the silicon. So these are also having 4 set of electrons. But here what is happening, we are using a P, that is a pentavalent impurity. You can see the last point over here. Okay, so in here you can observe that 4 are getting covalent bond quite well. They are doing pretty well. But now the impurity that you have added, it has a free electron over here. As the impurity is having a free electron, it is basically a donor element. It's a donor. Because electrons because as I said, holes doesn't exist. It's a virtual element. So here what is happening, the impurity has a electron which is free, not the silicon that has a free. The boron has the impurity has a free electron, and that free electron it is donating for the avalanche of transfer of electron and hole pair. Because this electron, when it is roaming freely, it will try to get accepted by some holes. Somewhere it will be generated. So that type of case, okay, the pentavalent, when a pentavalent impurity or a dopant like the arsenic, the phosphorus, here the phosphorus is being used, phosphorus are used, we call it the N-type semiconductor. Please make a note of this, okay? So N-type semiconductor means it's a donut type, it's donating the electrons. On the other hand, always we consider that plus is a accepting. Okay, so acceptor type is basically the P-type semiconductor where the trivalent impurities are used. Don't ever forget this. Okay, pentavalent impurity for the donut type or the N type, whereas the trivalent impurity for the acceptor type or the P type. So boron, gallium, aluminum, those are some of the elements, some of the impurities which are usually used with respect to extrinsic semiconductor to make it either N or P. All right. Any doubt till this point? Any doubt, anyone with this type? So we have discussed the valence band electrons. What is valence band? We have discussed valence band electron. We have discussed the different materials with respect to the energy bands. What is a valence band? What is a conduction band? When do we have a scenario where the valence band electron can move up to conduction band? When it can't? Okay, so that also we have discussed. Also now, along with that, we have discussed the semiconductor in 2 different ways. One is the intrinsic semiconductor. The other one is an extrinsic semiconductor. In intrinsic, as we have discussed, it's basically a pure semiconductor, but the conductivity will be very low, very small. Whereas in case of extrinsic semiconductor, we are adding up a dopant. We are adding up a impurity on the crystal of the pure material, and that makes it either N or a P-type semiconductor. Okay, and that's what we have studied so far. All right. Anyone having any doubt till this point? No.
No, sir.
Great. Let's see whether you have understood this correctly. Then we can understand. Let us see whether you are able to see it. So when you are considering an N-type semiconductor, what should be the majority carrier? Definitely N-type is the donut type. Okay. So N-type means it is an electron, more electron is there or more free electrons are there. So definitely we can say that electrons will be the majority carrier with respect to n-type, whereas holes will be the minority carrier, the convention over here. On the other hand, so majority carrier will have a current, minority carriers will also have a current. All together, whatever the current we are getting, that will be the total diode current. We'll see the calculation later, not today, but that is basically, so although minority carriers will have some amount of less impact, but the majority carriers will definitely have the more impact, because anyway, the more the electrons are generated, okay, that electrons that happens to be the majority in n-type. But if it is p-type, the electrons are less, it will be acceptor parts. The hole will be more, hence it will be the holes will be the majority carrier, whereas the electrons will be a minority carrier. Keeping that in mind, okay, there is some law, it's called as mass action law, which states the product of concentration of free electrons and the concentration of holes is constant under equilibrium condition, which is independent of amount of doping by acceptor or a donor intrinsic. What does that mean? That if I consider an extrinsic semiconductor where there is some, be it an n-type or a p-type, the product of holes multiplied by the hole concentration multiplied by the electron concentration, this will be equal to Ni square, where Ni is the intrinsic concentration, which is function of the temperature. What is Ni? Ni is nothing but when the crystal was pure. So whatever be the count of electrons which we are supposed to, or whatever we are supposed to get, even with extrinsic, the number of electrons and hole, whatever the pairs we are generating, the product of it will always be constant. Now, can anyone tell me the last thing, that how is it possible, that why is this law true? Can you guess? Can you prove that by some analogy, that why is this law true, that the product of concentration of free electrons to that of holes will always be constant? Can anyone try it? Anyone? From your understanding up till this point, since you said you have understood everything up till this point, so you should be able to answer this as well.
So may I?
Sure. You introduce yourself and go ahead.
Yes, sir. My name is from Vishal. Sir, one guess that I can take is the number of electrons exiting its position is equal to the number of holes that are being created.
Absolutely.
So
Correct.
I guess that is a constant measure for these two, and so that the product
But
is also
But
constant.
if I say the more the number of electrons are generating, or if in suppose it's an n-type where more free electrons are there, so don't you think that the more electrons will generate more number of holes also? Like it will try to combine with more number of holes itself.
So it will, but if we take the example of like the P type, it only has 3 holes. So no matter how much the N type affects it, it still will occupy only 3 holes at a time. So I mean in that order. So
Correct. Correct. Anyone similar answers or anything that you want to refine a bit?
So the number of holes will also increase.
So so you're saying the number of holes, yeah, that in a way, what I meant by this law is that whenever we are looking at n-type, suppose you are applying this mass action law in an n-type semiconductor, what will happen, that the more the electrons, the more the holes will also be generated, right? Like it's a proportionately, because we have to keep the balance intact. But whatever happens, okay, whatever happens, the electrons will combine with some of the holes. But even after that, what I mean is that the majority in an n-type will be the electrons itself. Holes cannot be greater than the electrons concentration. So eventually what I mean is that for a product of NP, if the number of electrons are more, the hole concentration is less. Okay, so that is what we are considering over here. Similarly for p-type, if the hole concentration is more, the electron concentration is less. So in a way, it is keeping a balance. It's not that both the parameters are increasing. It's not that. Either holes is increasing, the electrons are less. That's why the holes are there more, because the electrons and holes are not combining. That's why the holes are more, right? So n-type, more electrons means even after the free electrons were generated, some of the electrons have combined with these holes. But even after the recombination, there is some amount of free electrons which are present, right? So that means whatever happens, the electron concentration will be higher compared to P. And P-type, it's the reverse one. So that is why this particular law, mass action laws, whatever it states, the product of the concentration of electrons to hole is always constant and an equilibrium condition. Right. So this is one of the factors that we are. In fact, we will do some numerical in which you will find that this law will be very helpful. We are going to find out what are the concentration of the electrons and holes for that matter. Right. So we'll start off. We'll end up another segment. So we're done with the basic principle, the basic terminologies, the extrinsic semiconductor and how it works. Let us quickly dive into what will happen when we sandwich both the n-type and p-type together, because now we know what is majority carrier, what are the flow in individual extrinsic semiconductor, which element is the majority, which one is the minority, those things we have discussed. So now what will happen if I club together both? So you can see if a junction is formed between the sample of p-type and an n-type, we usually call it as a PN junction diode or simply junction diode. This is the basic of principle. So individual element, there is an n-type semiconductor, there is a p-type semiconductor or p-type extrinsic semiconductor, and we are fusing it together. So in that case, what will happen that whenever it is forward biased, we'll see that what is the diagram for forward bias. If that is a forward bias, we'll have a conducting current. But if it is reverse bias, we have actually no current. Okay, so as I was telling you that this operation, if you observe, okay, this operation that you observe actually allows the current to pass in only one direction. So is it not like something like a switch that allows the circuit to be on or off, right? And you will also find that there will be a few more diodes that will come in that will also be act as a voltage regulator as well, controlling the voltage. Okay, whenever you are using it like for a very high voltage supply, you will just use a very small little diode and it will restrict or it will arrest the voltage to a very good level due to the property of the semiconductor itself. Okay, so that is, you can see in practice as the n-type Si crystal is being grown, the process is abruptly altered to grow a p-type semiconductor Si crystal. Finally, a glass or plastic coating is placed around the joint crystal, and this is actually the diode how it looks. When you are coming back over here, you will be actually working with a real diode and we will see how it works. All right, but for the timing, this is the symbol. Usually the symbol, I think the symbol is there in the next slide. Yeah, this is basically the symbol of a diode. Register, just like we are a symbol, this triangle shape is usually referred as plus, and this vertical line will indicate the negative. Okay, so this is how it looks like in a real life. All right. So if I go directly towards the diagram of forward bias, where we actually might end our discussion with, you can observe that we have a power supply over here, and the plus sign is added to the p-type. You can see there are two types, p-type and n-type together. So the p-type is connected by this plus supply, whereas the n-type is connected by this negative supply. So this particular part, what happens, the process, what happens, that whenever this plus supply comes in over here, in this p-type, what is the majority? Majorities are the holes. Whereas in the n-type, the majorities are the electrons. So whenever this plus is coming to this end, this junction, connecting junction, the holes over here will be repelled. Like holes won't move, right? Holes is not a virtual, as I said, it's a virtual element object we are considering over here. So if I consider the other way around, the electrons over here, which are present, which are majority, they are getting repelled by this negative terminal because this is negative. As it is negative, the electrons will be repelled, so they will move towards more and more towards the junction. So this particular segment that you're talking about, I am trying to focus on. We'll come back because this is a very important segment. So it is going towards this part. Okay, as it goes towards this path, it will get and combine amongst all the holes which are present over here, because holes will also be concentrating over here. Why? because the positive is actually making these holes to move in this direction. Got it? Because it is repelling the holes as well. So during this specific portion, this small little segment will be filled with holes and electrons. Some of them naturally will recombine together, and in a way, this movement of electron, okay, movement of electrons from one place to another will indicate that the current will move in the other direction. So the current, you can see that this is the flow of current that will take place. You can see in this diagram as well. So the current is moving like this. This is a supply, it goes like this in some diagram. So whenever the electron is moving in a direction which is getting repelled by this negative terminal, the opposite way around, the current is actually being observed as a movement. Okay, so that is being discussed over here. So this is called as forward biasing when we are allowing the current to pass. You can imagine in the other way around, if I change the supply voltage, okay, if I change the supply voltage and I keep this as negative and this as positive, all right, so what will happen? This negative will attract the holes. So the holes will be coming more towards this portion, this junction, whereas the positive will attract the electrons more closer to this junction. So what will eventually happen? You can see that in between this, the junction which was present already, where the p and n types have been sandwiched, here there is no electron or hole pair which is present. All right, so you can see the electrons from n side. Yeah, please.
I have a next class.
I know. I will stop here itself. Very sorry. I'll stop it. Just give me 1 minute to wind up the session. So we will stop with reverse bias only. Okay, we will not do the reverse bias anyway because of the time constraints. So let us finish off on that note. So we will come back on next day's class. All right. So we will start off in reverse bias and we'll see how this junction that I'm talking about plays a very important role, okay, for the analysis of that. Okay, so that we'll discuss next week. So thank you everyone. I'll stop recording. Sorry for keeping you waiting, and we'll come.